Hello everyone, I'm Zhang from Johns Hopkins. I'm glad to present our work on solving a nonlinear blind inverse problem for tangled MRI using physics and a deep generative prior. With a MRI scanner, you can non-invasively imprint a periodic pattern onto the tissue, and then when the tissue moves, the text moves with it. It has been the golden standard for non-invasively measuring the internal motion in the brain, heart, and tongue. The main technical theme of tangled MRI is to estimate the motion. For 30 years, the field has been trying to solve several challenges separately. Tag pattern fades over time, which breaks the brightness constancy that optical flow approach relies on. So the prior work resorted to the Fourier-based approach, like a harp and phase-based optical flow, but the spectral overlap between the anatomy and the tag pattern degrades the results. Clinically, people usually need a separate cine scan just to see the underlying anatomy, so there has been a lot of work on synthesizing the cine images from the tagged images. And the image resolution is poor, so people have worked on super resolution. For decades, this field has treated these tasks as different problems. Our key insight is that this task and challenges are actually coupled. You cannot solve one well without solving the others. Our key contribution is a unified formulation that solves all of these tasks simultaneously in a nonlinear and blind inversion framework. Here is what the input and output look like. Given a time sequence of tangled MRI, which is acquired in low resolution, we inversely estimate the point spread function of the imaging system and the Lagrangian motion field over time, and the high-resolution cine images over time. We model the tagging process with a forward model. The anatomy is modulated by a fading tag pattern, then warped by the motion, and then blurred by the imaging point spread function. Then it finally produces the tagnet data that we observe. Each component is parametrized and grounded in MR physics. The challenge is that everything on the right-hand side is unknown and is what we want to estimate. This makes this a nonlinear blind inversion problem. So we minimize the reconstruction loss to estimate all of the parameters jointly. We solve it with what we call CDDP, the coordinate descent with diffusion prior. So we alternate between sampling anatomy from a pre-trained DDPM and updating the remaining parameters by maximum likelihood with a global optimizer. When we update one block, we keep the others fixed. The result is that the unified model outperforms every specialized baselines. We evaluate three outputs: the estimated high-resolution cine image, the estimated point spread function, and the motion. So for cine images, we compare the synthesized cine at each time frame against ground truth and report SSIM and PSNR. The simple low-pass filtering gives blurry results with aliasing artifacts because the nearby harmonic peaks leak into the filter. Our synthesis is sharper and much closer to the ground truth. We also show that we recover the imaging point spread function accurately in all three dimensions. For motion estimation, ours is more accurate and it is diffeomorphic in terms of the negative Jacobian determinant percentage. In the ablation study, we remove three components: point spread function, modeling of fading, and this optimization algorithm CDDP, one at a time to examine their contribution and confirm that each is necessary for the best result. In particular, when we replace the CDDP with a joint optimization using Adam, the optimization fails. We believe it's due to the ill-postness of the problem. So the takeaway of this work is that by combining the MR physics with the diffusion prior, we can solve the challenging inversion problem that previously considered impractical. And this work presents a promising paradigm shift in how to analyze tangled MRI. And this approach is training-free. which is practical in domains where such acquisitions are scarce. And we also find that the coordinate descent and the global optimizer sometimes is the key to solve this non-convex inversion problem. And let me know if you have any questions. Thank you.